Hello, good morning, everyone. Before we start for the day, I wanted to give some details about the project presentations. So first of all, there's a lot more groups than I've usually had. There's 25 projects, and so they're gonna end up having to be shorter in order to fit everyone in. I'm going to be asking for briefer presentations, aiming for like 8 minutes or so. So please make sure to keep it pretty brief so that we can get through everyone. The order of the presentations is going to be posted on Canvas. I'll try and do that later today. You have to submit your slides to Canvas by the start of the first set of presentations, so next Tuesday at 10 a.m., even if you present on Thursday, so that everyone has the same amount of time. I won't be asking questions during class, but I'll provide feedback to you guys later. I'll message it to you. And then a basic sort of slide outline that you could do for the 8-minute presentation. So title slide, data description, the modeling approach that you're taking. So what modeling strategies that we've discussed over the last quarter that you'll be using for your project, and then any preliminary results that you have. And then lastly, if you want to have ongoing ongoing work for the report, and talk about what upcoming analysis will be done. And yeah, like I've mentioned this before, but you should take the opportunity here to make the presentation more as intermediate step. It doesn't have to be super finalized for the project. And it's an opportunity to get feedback from myself as well as clarify the project for others. Question about the final report. When is that due? That is a good question. Is it in the syllabus? Let's check real quick. I'm like mixing up dates of the final report for my other class that I'm teaching right now. I want to make sure. Not here. I think it might have been in this set of slides. Yeah, due June 13th. So it's the Friday. It's the Friday of finals week. So it's due in about 2 weeks. Any other questions about the final report and final project?
So just to be clear about the presentation, that's due on the 9th?
No. Oh, wait.
Second.
Yeah. It's due next week because we are, yeah. So hopefully I updated the syllabus, but I'll make another announcement just to make sure everybody knows. Yeah, I'll put that in the announcement for the order of presentations. But we had asked, or I had asked you guys if you would prefer to have the presentations 1 week earlier than the first syllabus had shown, so that you guys would have more time to incorporate feedback. And so I think most people were on board with that. So we're going to do our presentations next week. Okay, any other questions? Um, Today is actually going to be basically my last lecture for the course. So I did want to remind everyone to please submit course evaluations. How can the course be improved, both teaching style and material. Yeah, your feedback will help make the class better for the next set of students who take this class. So I would appreciate any feedback you have to give. Okay. So let's go ahead, jump on over to our last lecture of this quarter. Apparently my pen is running out of battery, so hopefully it'll last long enough for this lecture. Okay, so today we're going to talk about another technique of classification. This is a classification technique commonly used in a lot of machine learning applications. And it's specifically for looking at binary outcomes. There are ways that you can look at multiple classes. And the analogous thing would be like a two outcome logistic model. It wouldn't be a multinomial logistic model. There are ways that you can look at multiple classes, but I would say it's a little more janky, a little less developed. It's the techniques is mainly focused around looking at binary outcomes. So I guess it's a little bit out of order because we're kind of jumping back and forth between methods that do more regression-based approaches for continuous variables and classification. So here we are expanding a little bit on the territory of when we started with logistic regression, looking at LDA and looking at KNN, and even k-nearest neighbors, and even last course, the neural networks is able to actually do both. But I would say the next sort of step for moving back in line with the logistic regression is the topic of today, which is support vector machines. So we're going to build up our knowledge again about this. So starting with description of a hyperplane. Okay, and so this is defined as a flat affine subspace of dimension p minus 1 in p dimensional space. Okay, so the formal definition is a little wonky, but I think if I draw a little example, it shouldn't be too complicated here. So if we've got x1 and x2, and we have a set of points like so, the colors represent your outcome classes. So you've got this, and that might be equal to 1, equal to 0. So the hyperplane, this is a hyperplane. It is in 2 dimensions. It would be defined mathematically as follows. So this equation generically describes a hyperplane, which we can see is an or the application of which in this example is being used to separate these 2 groups of points. Okay. More generically, in p dimensions, we have beta 0 plus beta 1 x1 plus beta 2 x2 beta p xp equals 0. And this lets you this lets you have a hyperplane across an arbitrary number of dimensions. It's a lot sort of harder to visualize once we're getting beyond a certain number of dimensions. But hopefully that you can see in the 2-dimensional case the sort of functionality and purpose of this hyperplane. So going back to, let's make a new sort of example. Oop, that was a horribly not straight line. Also not straight, but that's all right. So I'm just going to toss in a couple points here and a couple points here. If I want to draw a line which separates this, it turns out that if I am able to draw a separating line or a separating hyperplane, then you actually have an infinite number of hyperplanes that can separate your points. Infinite number of separating hyperplanes. Okay, and so I kind of liken this analogously to a linear regression, right? If I have a whole bunch of points, so okay, just to clarify so that we don't get confused in the notes, this is X and this is Y. In a linear regression case, before I formally do the regression and I want to draw a trend line, I can draw many sort of different lines through here, right? And so analogously, there's a question of, in the ordinary least squares method, we chose a specific line on the basis that it reduces the sum of the squared errors. So similarly, we have a decision to make in the case where you want to draw a hyperplane that separates these points, right? And so the technique which is done that we're building up to the support vector machine is starting with what is known as a maximal margin classifier. This is also called the optimal separating hyperplane. So this is a separating hyperplane that is farthest from training observations. Okay, so if I were to attempt to draw an example, say I have some points that look like this. Okay, let me get rid of this one actually. There exists a line. I have to draw this somewhat accurately. That maximizes the distance perpendicular to the nearest points. So imagine that these are all the same sort of distance. It kind of looks like the blue one is a little bit closer. So let me draw that like here. So this hyperplane maximizes this distance. And there's something a little bit interesting about this particular example. What you'll notice is that the hyperplane is essentially being defined by these 3 points. And in fact, it is, we call it being supported by these 3 points. And so this is actually called the support vector, because you can almost think of it as this line being propped up by points on both sides of your outcome. The other thing to notice is that besides the points that are acting as a support vector, none of the other points play a role in defining this line. I could have a huge density of points right here. And then these ones could be super spread out, right? And that has no bearing on the creation of this particular hyperplane. So I'm going to provide the, for context, the mathematical procedure for how to obtain the coefficients for this particular hyperplane. But don't get too bogged down in the math. I think it's mainly going to be to show the step-by-step developments as we, I guess, improve on this model, or what the sort of evolution of it is. So okay, hopefully this will all become a little bit more clear in a little bit. So this is a sort of formal optimization where we maximize this thing called M. So beta 0, comma, beta 1, comma, dot, 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 to beta P, and then M. So M is actually also a decision variable such that, so the constraints of the system, the first constraint, so 1, and then the second constraint looks something like this. Okay. So for those who are familiar with an optimization, this is the optimization system that you would solve in order to obtain the betas that define your hyperplane. It is similar in principle to figuring out the betas for a linear regression. If I were to write it out into like a formal optimization, it would look like this. So this is more kind of for your reference, and we'll touch back on it in a little bit, just so that we can see how it gets modified. But don't worry too much about the details of what's going on behind the scenes here. And I'll actually jump back to it in just a second. We've got two sort of issues with the maximal margin classifier. So I'm going to abbreviate this as MMC. So one, non-separable cases. So this is very common. So let's imagine a case where I have x1 and x2. And let's just go ahead and draw our points again. Okay, so in this case, what happens if I do something like this? There exists no linear hyperplane which can separate these. And so this is called a non-separable case. And as you can imagine, this is, in real world data, very, very common. In fact, it would be pretty uncommon to get perfectly separable cases. The second one is a little bit more nuanced. So two, sensitivity to individual observations. So let's consider I'm going to try and draw two identical plots here. So something like this. Okay, and then these ones don't really matter. And let's draw something like this. Okay, and these guys don't matter. Here, let me draw a MMC hyperplane, something like this. But if I were to add a single point, okay, so if our original line looks something like this, let's suppose I add 1 point here. That may change the hyperplane to look something like this. And so a single point can have a large effect. Okay. And so one of the ways in which this is dealt with is with a technique. So let's see. So our first technique was the maximal margin classifier. And in order to deal with these sort of apparent issues, it was or the support vector classifier was developed. And some of the features that are nice about this is that it's general robustness to individual observations, and a better classification of most training observations. Not all, but okay. So it has a similar optimization as MMC, but some modifications. So I'll jump back over here. So this is the set of, or this is the optimization for the MMC. And what the support vector classifier does is it adds a new set of decision variables, epsilons, through epsilon I. And it adds a third constraint, and it modifies constraint number 2. So actually, let me just write that first. So it looks pretty similar over here. And in fact, this part stays the same because it is simply defining my linear hyperplane. But then you have a slightly different term here. And you add a third constraint which looks something like this. Oops. Okay, so what is going on here? The way that I would sort of describe this is this epsilon is acting as a slack variable. So epsilon essentially tells you how many points can violate the margin. And so when I talk about the margin, I am specifically referring to, let's see here. In this plot that I showed, this this line, or these two lines describe a the margin. Okay, so you can't, in the MMC, oh, okay, sorry, I think I missed a question from a while back. Let me finish up this thought and I'll address the question. So in this particular example, the margin is defined by the points, and so you can't actually have points inside of the margin, because by definition the margin is essentially like the buffer zone that keeps those points out. But in the support vector classifier, by having this slack variable, you're essentially saying it's okay not only for points to be within the margin, but you could actually even have points on the other side of, you can have points on the other side of the separating hyperplane. And there's some slack essentially that's allowed to happen there. And by doing that, you're solving both the problem of, you're solving both these issues, right? That you have non-separable cases, because now I can draw a hyperplane and I might have a margin here and a margin here. And then actually in this case, you would need to, you would actually need to have your margin be something like this. And now essentially your margin is allowed to contain points, and your margin is allowed to contain points from the other side. Okay, and then it also makes it less sensitive to individual observations, because I could simply have this as a hyperplane still, and then have some larger margin in which to include some points. So it improves the sensitivity to individual observations. Okay, and so that's actually, so addressing the question that came up, what does general robustness to individual observations mean? So when I defined it here, this is, this just means that single points don't swing the line as much as you would see in the MMC case. Okay, I know I'm kind of jumping around a lot, so sorry for the confusion. If we go back to this equation, okay, so we can see that there's some slack variable here. And then there's a different parameter C. So this is the tuning parameter, or we can think of it as a tuning parameter. So C, so this bounds the number of epsilons. So think of this as a budget for violations. This is really similar to a lot of the tuning parameters that we've talked about before. Essentially, this is saying, okay, if I have a larger C, I have a larger budget, and that allows you to have more points in the margins that are, violating the sort of rule for the maximal margin classifier. If C is really small, or actually if C is equal to 0, then it's essentially saying that you are not allowed to have points in the margin. And that will end up making it being the same as the MMC. So if C equals 0, then epsilon, so if C equals 0, then epsilon has to be equal 0. So this, let's see. Yeah, so this term ends up being 0. So this ends up just being M on this side, which is the same as the maximum margin classifier. Okay, so I want to show, since this is a lot harder to draw, I'm going to show an example from the ISLR textbook, which shows this property pretty nicely. So where did I put it? Here we go. So this is a support vector classifier, this line, and the dotted line is the margin. Okay, and so what you can see here is that the C is pretty large. Okay, it's got a pretty big budget for my epsilons. In other words, it's allowing lots of points to be in the margin, and not only that, it's allowing points to be on the other side. And in fact, we could even count, right? So there's, if this is kind of the red side and this is the blue side, you've got 1, 2, 3, 4, 5 violations, and then you've got all of these points within the margin. So that's when you have a big C. And let's decrease the C a little bit, which is going to tighten this up, and it's actually going to affect the hyperplane a little bit, but not by a huge amount. We can see the change from here to here, right? And you can see now that the number of violations, right? Here we had 1, 2, 3, 4, 5. Here we have 1, 2, 3, and then all the points. There are fewer points within the margin. So this is what happens as you shift your tuning parameter to be a little bit smaller. Okay, and so we can see again, if you tighten it up a little bit more, in other words, if you decrease your tuning parameter C, now we have 1, 2 violations, and then even fewer points, and then looking like this for the smallest one. So hopefully you guys can see the trend that's going on here as I affect my tuning parameter. Okay, and you might be thinking to yourself, how do I choose the value for C, the tuning parameter? It's the same conceptual approach. you want to choose the C which provides the best error rate in a testing sample. So similar to what we would do in like a k-fold for cross-validation, you would want to test against a testing set and figure out your error rate. And so, you know, this in the in-sample error rate, you can see actually the C is continuing to decrease. Okay. And then the next point that I wanted to show is actually right here. Here, if you have data that looks something like this, you'll find, okay, so the observations fall into my two classes again. And if I were to draw a boundary around it, I might draw maybe like some kind of circle or something, right? But unfortunately, one of the drawbacks of the support vector classifier is that it has to be a linear separator, right? And so in this case, you would draw a line that looks something like this. And unfortunately, it's going to perform pretty poorly because you've got a whole bunch of, you know, red points up here and a whole bunch of blue points down here. And so that's one of the sort of big drawbacks of the support vector classifier. And so this brings us to our, third and final sort of evolution, which is called the support vector machine. And so in this case, we could allow for polynomial expansion or interactions of x's. So that's, so when I was drawing this thing that describes my hyperplane, I could make it nonlinear, right, by having additional terms. I could do beta, let's just say 3x1 squared plus beta 4x1 cubed. And then you could even do, you know, interactions and interactions with polynomial terms. Okay, and so what you'll find that if I try to do this type of approach is that it's going to explode very quickly, and it quickly becomes computationally infeasible. One, because the sort of calculation of and solving of the betas becomes more and more difficult, and then two, and probably more importantly, is the sort of dimensionality will quickly explode, right? I could add an arbitrary number of different ways. And, you know, if I were to do this, you would be able to get some kind of nonlinear hyperplanes going on. But in fact, in practice, it's kind of clunky and infeasible and impractical to do it this way. So here, okay, it's kind of been a little bit difficult for me to figure out a sort of really handy way of teaching this, because so what a support vector machine does is it actually modifies and generalizes the computational step. Computation of the support vector classifier. And this is, I guess, one of the limitations of this course, is that we don't really get into the like theoretical aspects of how you carry out like computations and the sort of black box behind some of the algorithms. We do go into some of them, but not everything. And so it turns out in the way that you solve a support vector classifier is you actually have a pairwise kernel function that takes the inner product of points that are acting as your support vectors. And so I guess all I'll say about this is that support vector classifiers uses what is known as a linear kernel. And support vector machines can employ more complex kernels. And so common ones that are used are polynomial kernels and radial kernels. And this is going to be one of those topics where I'm going to introduce you guys to the concept, and if it's something of interest, you can dive a little bit more into it. And what I'm going to do now is I'm just going to show some applications of support vector machines in R so that you can get started to see how to conduct a support vector classifier or a support vector machine. And also you can see what it's doing, because I guess I'm being a little bit more ethereal here. You can imagine that it's essentially just making nonlinear classifiers. In fact, if I can go back to the textbook to show the example of the support vector machine, and you can see how it separates the data in the shown example here. So if this is our example for the support vector classifier, we can apply a support vector machine. So this is a polynomial kernel with degree 3, and then this is a radial kernel. And you can see now that it is successfully able to separate the points again. Okay, so let's take a look here. I do need to install this package. So E1071 is an R package that lets you do support vector machine classification. So full disclosure, I am actually using material from this data camp series for doing this example. Okay, so let's take a look. I'm going to create a plot here. These are just randomly generated points, and you can see looks something like this, and we want to create a support vector classifier. Okay, so I'm going to put this into a single data table called dat. And I'm going to do a svmfit.linear, which is just a support vector classifier. So again, looks similar to our typical regression setup, and then we're going to have a couple options. So here I'm going to have a linear kernel, which is what you would use for the support vector classifier. And then this is the C, the cost, which is the budget for my epsilon. And so the larger this number is, the more points are allowed to be violating. And we're not going to scale this. Okay, so I can, oops, did I load my libraries? Actually, I don't need this. Oop, didn't run this either. Third time's the charm. Okay, so we've run this, and I can take a look at the summary and see what this tells me. Great, okay, so this is a linear kernel for, it's a subset of the support vector machine, the support vector classifier. Cost is 10. It's got 6 support vectors, which means that the line that's being defined is essentially getting propped up by 6 points. And you've got 2 classes. And so let's take a look at what this looks like. Okay, so here's our line. And you can see this plot doesn't actually draw the margins, although if you guys go into this tutorial, they'll actually show you a customized plot where you can see where the margins are. And we can see that the classification allows for points to be on the other side, and then the X's are going to be, I believe, are going to be points that are contained within the margin. But nonetheless, the hyperplane that is acting as the separator for our 2 classes looks like this. Okay, so let's make a example for support vector machine using a radial kernel. So I'm going to load in some data, which I'll post on Canvas so that if people want to do this and follow along, they can. This data set is actually coming from a textbook called Elementary Statistical, or Elements of Statistical Learning, which is it's a counterpart to the ISLR book, which I've talked about. It is essentially the same content as ISLR. It's by the same authors, but it contains a lot more of the theory behind it, and it goes into a lot more of the statistical detail. So if you are really interested in the topic and you've gone through ISLR, ESL is a handy resource to understand a lot of the more technical background of basically a lot of the stuff that we've covered. And so, okay, don't want to go on too long of a tangent here. We are using that data set, and let's take a look at what that looks like. Oops, okay, wait. Hang on. Error not found. Ruh-roh. Oh, I bet it's because I am not in the right directory. Okay. This should work now. There we go. Okay, so we have these sets of points here, and I want to create a hyperplane boundary, nonlinear, that would separate these two. Okay, and so this is going to look pretty similar. Except now we're going to use a radial kernel instead of a linear kernel. And I can look at the summary. And see the kernel being used here. It's actually still got 6 support vectors. Actually, I'm a little surprised by that, but we'll see what it looks like. Whoa, okay, hang on. I think that's doing the original one, huh? Did I run? Oh, I used the wrong data. Okay, let's try this again. Ah, there we go. Okay. 103 support vectors. So let me go back to here just so we can see again. 103 support vectors, 2 classes, separates them into 49, 54. So let's take a look. Okay, Here we go. So you can see that you can get these fairly complex shapes out of using different kernels in the SVM. Okay, so, oops. Okay, there's a question here. Can we do more than 2 classes using this method? So yes, you can, but it's not doing it in any sort of analogous way. It's doing sort of one-by-one pairwise comparisons of the classes. No one has been able to figure out a good way of doing support vector machines for multiple classes, or I shouldn't put it that way. They're not able to simultaneously create a hyperplane across all the classes. I guess it's too computationally complex. And so that having been said, if you do want to understand the application of SVM to multiple classes, please, yeah, I guess I don't really have time to cover it in this course. So you'll have to kind of independently look into it. I would not recommend just running this code for a response variable that contains more than 2 classes without first understanding a little bit about the implications of doing that. And then the question is, the number of support vectors equal to the number of observations? No, it is not. The support vector, or the number of support vectors, again, you can think of the support vector as the sort of point that's propping up the boundary. So it's really hard to tell in this case what that is, but because there are like there's like a kind of margin that you can't really see here, and the support vector are essentially all the points that are defining that marginal boundary, because it's you can think of it as the points that are propping up the hyperplane, and so yeah, so the number of support vectors is not going to be equal to the number of points unless all of the points are defining the marginal boundaries. Okay. And that's what I have to say about that. Are there any other questions? Otherwise, well, let's take a 5-minute break, and in the meantime, I can answer questions if anyone has any.
Hey, Alan.
Hey.
Hey, could I ask a question on the homework?
Yeah, sure.
Yeah. Uh, this is regarding the general additive models. So,
Mm-hmm.
what is the idea when we are trying to evaluate the model? So, what is it that exactly we can do? So, I was able to find a couple of things related to this. So, I just wanted to confirm which would be the right way to go. So, yeah,
Okay.
yeah. So the first thing I was thinking was that we should evaluate the model based on in sample and out of sample mean square error, and then probably some of the literature, the, the modeling that people have done, they have also used some kind of a residual plot to see how good the model is, and some people have also used an ANOVA table to evaluate. These were three things that I was able to find out. I was just wondering which should be the right way to go about evaluating this model.
Yeah, so okay, so we're not talking about the purpose of the GAM. We're talking about how to measure the quality of the model.
Mm-hmm.
Yeah, so all three of those are valid approaches, and arguably are probably things that all of which you should be doing anyways to test for robustness. So yeah, I would say um, for the very first one, I guess it's a little bit different because I didn't really teach any way of recalibrating any parameters in the GAM to sort of account for the testing, but it's still a good technique if you want to do a comparative procedure against other sort of models. And so the main idea is, I guess the way I would put it is everything that you've talked about is sort of like, I could do a linear regression, I could do a ridge regression, or I could do, a general additive model. And the way in which I would compare the strengths of these and the quality of these models is by, looking at the residuals, like you mentioned, comparing how each of those does in predicting an out of sample, test prediction. All right, and so, if the linear model residuals don't look very random, but then the GAM residuals do look very random, then you have some sense that like the functional form is more accurately being captured in the GAM example. And then if the predictions are better for one type than another, then you can say something about the ability of one model to predict the outcomes, right?
Mm-hmm.
So does that make sense?
Yeah. So yeah, just to clarify, so in the homework problem particularly, so when you say you evaluate the models, so are you just expecting that we look at GAM model graphs and then try to say which variables are maybe linearly dependent and remove those variables out from the smoothing function and then redo a GAM without those variables? So is that something you're looking at?
The last one is that
You are saying that is for the last one. So and explain the results, evaluate the model of in the second last point. Evaluate the model.
yeah. Yeah, so basically look at how well it predicts, right? That's essentially all it's asking for.
Okay, so the mean squared is the one I should check for between the testing and the training data.
Yeah, yeah, and you can explain, you know, kind of what it means and generally how it's performed. Yeah,
Okay. Okay.
I would compare it against um the linear model.
Oh, okay.
Yeah.
Fine. Thank you.
Okay. So we've just about covered all the material. I'm gonna jump back over to the whiteboard, and I guess what we'll do to wrap up the class is to take a step back and do a quick overview of the topics. I know it's been definitely like a flurry of material, so I wanted to give some kind of higher level structure to everything that we've sort of learned. And so what we're doing, so what is this class? It is talking about, you know, statistical techniques or econometric or machine learning techniques that we can use and employ to analyze data, right? And so what I've been trying to do is to basically fill up your toolbox with a bunch of techniques, some of which you may be familiar with, some of which hopefully is new to you. And you know, this isn't like a course that gets heavy into theoretical detail. And so the, you know, main thing that I would caution is that if there are things that you find make or if there are techniques that you think make a lot of sense for your research, it may be a good idea to dive a little bit deeper than sort of the cursory look that we've gone over in this class. But even sort of taking a step back when thinking about data analysis, I do want to emphasize that that you shouldn't just get a data set and start diving into running these more complex regressions. Oftentimes it's kind of this step-by-step process where you want to first look at the data, you want to explore the data. Even simple sort of summary plots and summary statistics can tell you a lot about how you should approach doing the analysis. And I'm hoping that sort of the way a lot of the homeworks have been laid out can have sort of guided you in that sort of procedure. But remember, it's always good to get a exploratory look of the data before you dive into these more complex statistical analyses. Okay, so we're going to talk about regression, techniques, and classification techniques, which I don't know why someone came along and decided to separate these two, because technically this is still technically regression, but okay. And we have kind of divided this into, you know, linear approaches and nonlinear approaches. So we've got our typical model, y beta 1 plus epsilon. Okay, so hopefully everyone knows what this is, our error term, and what this is. Right, it's the slope of our line, and everything is sort of building up from this. We've talked about traditional comparisons. where most people talk about standard errors and R squared, but there are lots of other metrics that are just as, if not more important to consider. So one, check residuals. Right, if we have residuals that look like randomly scattered like this is good. If we have residuals that look non-random, this is bad. For model comparison, say we had y equals beta 0, beta 1, x versus y equals alpha 0 plus alpha 1, x 2. Don't just compare R squared, look at the mean squared error. And really, you know, what we're talking about here is you made a model that predicts an outcome. Which model produces the best predictions? And the model, the metric with which we measure this is the mean squared error, not the R squared, right? One of the most crucial concepts that we talked about are the components of our error term, which is equal to bias plus variance plus noise, but we don't really talk about that. And so in our error, so total error, we have model complexity, your bias will go down, but your variance goes up as components of your error term. Okay, that was a terrible line. Let's try that again. So this is our total error, which is the combination of these two. So we want to aim for here. Also, I'm going through a lot of this stuff pretty quickly, so feel free to speak up or write out in chat if you want me to talk about something a little bit more or you're confused. And one of the ways that we really sort of harp on being able to get an accurate measure of the total error is to do everything out of sample, so cross-validation, which is a generic procedure, as we've seen, can be applied across a whole set of different approaches. So we split our data into training and testing, and we use the training to build our model. And then this is used to predict outcomes if we combine it with the testing. And you can do this to iterate to improve model. Okay. Next is subset selection. How do we choose variables for model or identify important ones? And so we've covered a whole bunch of different techniques. So one, stepwise selection, choose model by R squared, and then choose best by AIC, BIC, adjusted R squared, or even cross-validation. We've covered shrinkage. So ridge regression, lasso regression. And then we even looked at some examples of dimension reduction. And so this was principal components analysis. Okay. And so here we have now sort of covered ways in which we think about the quality of the model, and then ways in which we can build up the model, right? How to select specific variables or measure what variables are important for the model. And then we can depart from our linear approaches and think about non-linear.
Alan, can I ask you a question?
Yes.
Yeah. So when you go about selecting the right variables for your model, so do you think that shrinkage methods are slightly superior when you compare that with a forward selection using AIC or BIC? Because with shrinkage, the model takes care of all these bias variance issues.
Shrinkage, you're saying? Shrinkage models.
Yeah.
Yeah, I mean, they're sort of
Yeah, so I'll just rephrase my question. So my question is precisely that the stepwise selection will not consider the bias variance trade-off, unlike
no,
what shrinkage does.
no, it does. It definitely does, right? It uses it. So you could use cross-validation as a metric to select the variable, right? So the bias variance trade-off that we're talking about is, should I put in more and more variables? And the more variables that I put in, the more complex it is, and the more likely that you're going to start overfitting the data, which is exactly the whole issue with the bias variance, right? Is you're increasing the variance component of the error term too much. So all of these metrics are ways in which we are directly kind of addressing this bias variance trade-off, because the AIC and BIC and adjusted R-squared all sort of penalize you for having more variables. So it's kind of an indirect way of doing it, but it definitely takes into consideration like essentially a penalty term for having too many variables. So the stepwise selection does, it does consider that. Whether or not, you know, a stepwise selection is necessarily better or worse than shrinkage, you know, I would say it's more on a case-by-case basis. You know, people, I will say that the choice in which you pick a model is often informed by kind of what your sort of knowledge and comfort with specific techniques. So I'm talking about in practice, right? Like people don't run models where they, you know, and I don't even know if you necessarily should, but people don't do every combination of possible like methods. Like first I'm going to check against stepwise selection forward and backwards, and I'm also going to check against ridge regression, and I'm also going to do lasso regression, and I'm also going to do principal components analysis, and I'm going to do like out of sample testing and make sure I'm going to pick exactly the best model for exactly this right context, right? It's more, oftentimes it's more about what people end up being more familiar with, or how they learn the material. And so I'm not gonna kind of sit here and say that you should do one or the other. Oftentimes I think it makes sense, depending on the context, to choose one particular model. And it's kind of hard for me to describe the like conditions under which you would do that. It oftentimes comes down to experience. What I would say for a lot of so in your shoes and a lot of the others folks in the class who are learning about this for the first time is, you know, think about, as you do analysis, you know, either for the project or in the future for your research, like think back to how you've gone about, you know, doing some of these techniques in the homeworks, what you think kind of makes sense, and build up your experience, you know, practice with different techniques and until you get comfortable with them and you have a good sense of the strengths of weaknesses of any, you know, particular set of techniques, right? So the more you employ tools in your toolbox, the better you get at using them. Yeah, so I don't know if that necessarily helps.
Yeah.
I would say it's so I guess what I'm trying to point out is that, like, I'm not going to tell you like you should use this model in these X times and you should use these models in these Y times, right? You should be building your experience with a lot of these so that you know yourself when the best time is to use them.
I was kind of, this was related to my project. So we chose a data set which has got 300 odd variables. So we are finding it tough to cut down on some of them.
Yeah, exactly.
Yeah.
So this is a good point, right? So like when you're talking about having many variables, like doing forward and stepwise selection can start to get a little bit cumbersome. And the nice thing about the shrinkage is that it like works through all of these automatically. And in fact, you know, once you're getting to really large number of variables, one of the more efficient ways of tackling those problems is to use things like neural networks. I'll sort of, you know, point out that's one of the reasons why those techniques were developed in practice, is to be able to deal with a large number of features.
Okay.
And I think the ability to deal with that large number of variables, when you have so many variables, let's sort of back up and think about this in practice. Like when we talk about this ongoing sort of debate about inference versus prediction, you often don't want to really think about inference when you're doing huge numbers of variables, right? Because it means that you're not necessarily caring about the effect of any one particular variable, which I could measure more efficiently, I guess, in a more classical sense of eliminating other variables. You care more about getting predictive outcomes. And so the techniques that do those types of things are focused on prediction rather than inference, which is why, like a neural network, you're not going to be able to say anything about the weights, right? You just care about what the model predicts. So definitely think about that in the context of your problems. If you want to look at the effect of a particular variable, or if you want to look at or developing a model that's able to predict outcomes with greater accuracy and precision.
Okay, thank you.
Yep. Okay, so nonlinear approaches. So we kind of built this up, right? Polynomial, piecewise. So this would be, you know, how many xn, how many breakpoints, and then this was further developed into splines, cubic versus normal, how many knots, and then smoothing spline, which has a knot for every point, and then we have a parameter, a tuning parameter, how to choose lambda. And the answer to all of these questions, right, is cross-validation. So this is kind of one group of techniques that we did. A separate one is kernel regression, how to choose bandwidth. And then the final one, which we covered last time, neural networks. So we looked in particular at feed forward, and this is how to choose hidden layers and number of nodes. Okay, and so this is sort of the set of nonlinear approaches that you can take, and sort of wraps up our sort of discussion about sort of continuous variable regression.
Alan,
Yes.
our recent homework, the problem 2, so that's a look at like the nonlinear approaches, correct? So
Yeah, that's right.
like kernel regressions. So I'm trying to wrap my head around, like, when we talk about nonlinear model, do we, like, we can have multiple explanatory variables, but what it means is like the relationship between these explanatory variables and y is like a polynomial, and like such as like a square or like a cubic. Is that the distinction?
Yeah, so that's polynomial like this, right? But it could be more complex, right? Which is why we use splines and smoothing splines in kernel regression. and neural networks.
Okay.
Yeah. And so if you think back to that example where, you know, I had this sort of set of points that look like this, right? And then, okay, I'm just gonna draw more points. And then we fit, you know, lines that are able to do that. Yeah, you know, if you do like polynomials, like you can create lines that are nonlinear, but sometimes they get so complex that, and there are like certain drawbacks of doing the polynomial approaches and having a lot of them, right? One of the things that I talked about is particularly at the boundaries, you tend to get these like oscillating effects, or like weird things that happen.
Right.
And that's why splines and kernel regression can really sort of help with that.
Okay, that makes sense.
Yeah.
So when we think about like cross validations on nonlinear approaches, is it the same principal concept where, you know, sort of what you were trying to get us to do in the homework, like divide the data up into training and testing?
Yes.
And then, okay, so the concept and principle does not change in linear versus nonlinear approaches.
That's exactly right. Yeah. So like, so think of it this way. Okay, let me clear this out. So let's say I fit a line through here. And then I have a testing set of points. Maybe that looks like this. I can compare, right, against, I can measure how well my model does at predicting out of sample from what I've calibrated. It doesn't really matter that that line is straight, right? I could run a nonlinear model and get a line that looks like this, and then I could measure how well that line does against the predictions, right? So the principle is the same, you're just creating a different sort of fit to the data. And that's why cross-validation is such a powerful tool, is that it can universally be applied to any model that fits data.
Okay, makes sense. Thank you.
Okay, and then let's wrap up with, oops, what the heck did I do? Classification. Here we talked about logistic regression, and then linear discriminant analysis. And then we looked at non-linear approaches. And so here, this is our k nearest neighbors. The neural networks. And then just today, support vector machines. And so these are different techniques of classification that can be used and applied to essentially try and look at data where your response variables is comprised of discrete classes rather than continuous observations. Okay, I guess I already sort of touched on the prediction versus inference idea. And so, we have prediction versus inference. Oftentimes this is sort of non-parametric sort of approaches on the spectrum of things, going to parametric. And here we care about predicting outcomes, and whereas in the parametric we care more about causality of variables. Okay, and so I think sort of jumping back out, when we think about running these models, interpreting them, and contextualizing your results, think carefully about what the statistics say and what they don't say. Yeah, please, hopefully that the content of this course has helped develop in your mind, like a lot of the traditional things that people say, and this varies again from discipline to discipline, but I do find myself frustrated sometimes by people just saying, oh, the R-squared is really high, or the standard error is like the variable significant, right? That means something very specific, and it doesn't often mean what people think that they're trying to say about the quality of the model just by these metrics. Think about why something is important, what relevant things does it tell us, and also kind of know your audience, right? A lot of the stuff that we talk about is a little bit more complex and nuanced. So, the more experience and familiarity you gain with doing a lot of these procedures, then the better you are able to convey, findings and results to those audiences. Okay. So I think we're going to end here for the day, or I guess for the course, since this is the last sort of formal lecture. So thanks everyone for putting up with this online format. I know it's probably less than ideal and a little more difficult to concentrate and focus compared to a regular classroom. But hopefully everyone was still able to take away stuff. I do want to make a quick logistic announcement, which is, I've been making those more sort of detailed notes that I put online, but I'm definitely really behind on that. I'm not sure I'm going to be able to get around to creating those notes soon. So what I'm going to do instead is I'm just going to scan my handwritten notes and post those in each of the respective lectures, so that you guys will still have reference materials to be able to look at with regards to all the handwritten stuff that I've been doing over the course of the quarter. So those will be kind of like the last couple lectures. Otherwise, yeah, I hope you guys have had a good quarter. Just a reminder to do fill out those course evaluations. Those will be very helpful to me. Otherwise, I will see you guys next week for presentations. And yeah, looking forward to seeing what you guys do.
Thanks, Alan.
Yep.
Thank you.
Hey, Alan.
Yes.
I have a quick homework question, if that's all right.
Yeah, go ahead.
So, number one, the last bullet point about KNN. In the previous two, I used k-fold, but I'm not sure how to do that for k-nearest neighbors, or if that's like how you wanted us to calculate the test error, but yeah, that's in general my uncertainty with that question.
Yeah, so the test error for this problem, let's see. So you can still do k-fold, well, yeah, you can still do k-fold in the KNN case, right? Because you are like leaving out some number of points and then predicting what those are via what the KNN tells you. I guess the procedural part of it is a little bit different, but what I'd say for the test error is that you are not looking at the mean squared error, you're looking at the error rate. So,
Is that because right now I have calculated the ACC, is that on the right track?
okay, here, I'll show you. Let's say your actual versus predicted. Let's say you just have ones and zeros. It could be you know, multiple classes, but let's just go with ones and zeros for now. So you could have something like this as your outcome, right? And then your predicted outcome could be something like 1, 1, 0, 1, 1, 0, 1. And so these ones are correctly predicted. And then these ones are incorrectly predicted, right? Because this one should be a 1, but it's predicted as a 0. This one should be a 0, but it's predicted as a 1. So the error rate is simply, let's see, I got 2 out of 1, 2, 3, 4, 5, 6, 7. 2 out of 7. Does that make sense?
Yeah.
Yeah. So all you need to do is calculate the error rate for each of these things. So what you would do in problem 1. So in the third bullet point, you run LDA on the training model, and then you predict. So you predict on the testing set, and then you just measure the error rate of the out of sample predictions, and then you do the same thing for logistic regression. You train the logistic regression on your training data, and then you predict you predict on the testing set and measure your error rate, and then we can do the same thing for KNN. We can we take our data and then we predict that on the testing points, it'll give us what it thinks each of these points are going to be, and then you can measure which ones get wrong. And then so now you have this like uniform test error across all of the models. Does that make sense?
Yeah, that makes sense.
Yeah, and so the one thing that you need to keep in mind is you're probably going to get like probabilities out of the predictions for the LDA and for the logistic. So this would be predicted probability, and so it might be like 0.6 and 0.7 and 0.4 and 0.8, and then this might be like 0.3 and 0.51 and 0.6 or something like that. And so these translate into actual points. If it's basically the way I would do this is if it's like bigger than 0.5, I would assign it to 1. If it's smaller than 0.5, I would give it 0. So you give it the most likely outcome.
Okay.
Yep.
Hey, Alan.
Hey.
Wanted to also throw a homework question off you. I guess like for GAM, I'm first trying to like wrap my head around it. So like the model itself is producing what could be a combination of either like linear coefficients or these smoothing functions we've talked about. Right?
Exactly. Yep.
Okay, and so then like, well, I guess if you're like plotting the results, like intuitively, I initially thought I would just plot like my predicted versus observed. But if you're actually like trying to plot, somehow like represent the model, like how would you do that?
Yeah, okay. So this is one of the, I think, biggest strengths of the GAM is that it builds off of a combination of like the linear model and the splines that we were talking about. So it linearly separates each of the explanatory variables so that you can still have a direct relationship between your X and your Y. So what sort of outcome you're looking for should be something like this. Let's say we have 3 variables, x1, x2, and x3. So the real big sort of plots of interest are something like it should be deriving essentially a sort of functional relationship between your x's and your y's. And these are the this should essentially be the outcome of your GAM. So in a linear model, it just provides a beta, right? But the beta itself is actually describing like if this were a linear regression, the comparable plots might look something like this, like a line like that and a line like that. And we don't draw those plots because we just give the beta, and the beta represents the line. But in the GAM, because it's not linear and it's not easy to describe what the like relationship between the X and Y is you draw the line. So this is essentially like the beta representation of the relationship between X and Y for this like weird nonlinear thing. Does that make sense? So that's kind of what I'm looking for here. In R, there is an automatic way of producing these plots, and I would be very surprised if you weren't able to find a package that would do this type of thing, where you run the general additive model and then it would produce these plots automatically.
Yeah. Okay. Well, there is like a GAM package. In terms of plotting, like I think I was initially confused because like I thought I basically like I just need to sort out how to like apply these smoothing functions to a new set of data. Like
okay, yeah. So once you figure that out, the thing that I would that I'm kind of looking for in the homework is like, so in this particular set of things that I drew, like we can see these individual plots, and I think the takeaway from this is like, even if you okay, if I compare against a linear model, I can see whether or not like the linear assumption holds, right? And so for plots 1 and 3, I might argue that, hey, these look different enough from the line that you shouldn't be assuming linearity.
Right.
But maybe for x2, like it's close enough to a line where maybe I say it's okay to not do the smoothing because it's close to linear.
Gotcha, yeah. And then I guess to go off of that, so like let's say, just still using this example, the black line are the fits that you came up with using a training set. And then like if you were to apply this to a test set, then like those are the same values you would get, but you could imagine like overlaying the like true, like I guess I'm trying to figure out is like if you applied this to a test set, wouldn't you get that same, you would get the same graph, wouldn't you?
So this is kind of what I was talking about with Gene. So if I have testing points that are in this blue, there are going to be I can compare the strength of my prediction in black, right, versus these guys, and I can calculate my error, or I can compare them against the red line and compare that error. And those will give two different things.
Right, okay. But like in
so the line, so the line, the fits are what they are based on whatever you trained them on.
Right.
So you've got your red line and your black line, and then the out of sample test error is just going to be comparing new points against whatever you fit, either way, if it's linear or nonlinear.
Okay, gotcha. In that case, like you could report just like a residual plot as well then, right?
Yeah, absolutely. And that's one way in which you could solve issues of the residual plots is desmoothing. And oftentimes I think you're gonna find that you basically always get more random points unless the function is truly linear with in your residuals when you do this type of nonlinear smoothing.
Okay, but you wouldn't be able to, sorry, I meant like you could get a residuals from like when you were drawing the difference between the observed test blue data points to the black fit. You wouldn't be able to get a residual plot from that, I guess, right? Because that's like not a single, since it's not linear, you don't have like an axis to go off of, correct?
No, you can get a residual. Residual is just it's just y hat minus y, right? So you can predict.
Okay.
It's a little weird to talk about it in context of like a single x, right? Because there's like 3 x's in this case.
Right. Gotcha. Okay. Cool. I'll try and figure out how to do that on Python.
Yeah. There should definitely be a package, so you should be able to do that.
Yeah. All right. Thanks a lot.
Alan.
Hey.
I would like a homework question also.
Yes, go ahead.
So for like question 1, so while dividing like training set and testing set, is there any criteria, or I can just randomly divide like randomly put 75% of the data in training set and like randomly put like 25% of the data in testing set?
Yeah, you can do it however you want. Yeah, no requirements there.
Okay. So, and I do not know, like when I am predicting in like the multinomial, like logistic regression, it's giving me like in the prediction also, as you are mentioning, like it should give you like some type of probability value, but it's
Yes.
giving me like 0, 1 value also in the prediction function.
Okay, in the prediction, you have to specify the response type. So what I would do is look at the function, look at the help category for the function, and look for the response input. And you can give it as, you can return it as the actual value, you can return it as the odds ratio, you can return it as the probability. So the prediction is able to return different sets of things to you. If what you're interested in is the outcome of 0 or 1, then you're already set to go. You don't need to go through probability space.
Yeah, so when I'm using the predict function, it's already giving me outcome. And what I'm doing is checking whether this outcome is different than the original outcome. And based on this, I'm calculating the error.
Yep, that's exactly right. Yep.
Okay. So, and I have like a question regarding like the question 2, where, question 1, when we are doing the KNN, and like you are saying that which value of K seems to perform the best on the data set. So it's the value of K when the error is minimum.
Exactly.
So, and do I need to like, because I was like doing like 100 cross validation, do I need to look through like a different type of cross validation and then see which is this? And then like, is there any limit or just assumption?
No, it's, yeah, it's as long as you are doing some sort of cross validation, I'm happy.
Okay. And for question 2, I have this question is that when again like splitting the training and testing data set, I'm like I have to do like a linear model first, and then fit a GAM general additive model. So in this one, do I need to like do the regression twice? First with the regression, do it normally, and then see which variables are linear, which variables are non-linear based on the plot, and do the regression again with the linear variable with not smoothing and non-linear variable.
You just need to do it once.
Okay.
Yeah, it's more just to identify which ones are not linear, and then yeah, you don't need to rerun the linear model.
Okay, and then and when I'm doing this with the testing data set and like running the plot, I'm seeing that the linearity assumption is kind of changed for the same variable, as I think the data set is different.
Wait, say that again?
Because some of the variables, when I'm running the model on training data set, some of the variables were not linear, which I found from the graph.
Yeah.
And then when I run this same model on the testing data set, I think some of the variable become linear, some of the non-linear variable become linear, some of the linear variable become non-linear.
Yeah, that's
and
okay.
I believe it's due to the data set is different.
Yeah, exactly. And that happens, and that's okay. I wouldn't worry about that.
Yeah, so when you like ask for the which variable, if any, is there any evidence of non-linear relationship? So should I answer this question based on the whole data set or based on my testing and training data set?
Based on the testing and training, and you can, this is all qualitative, so you can talk a little bit about ones that are changing, and you may suspect that there's you know, maybe like the sample size isn't large enough, or they're like critical data points that are affecting the curve, that sort of thing. But you look at it qualitatively.
Okay, and when I'm doing the like stepwise regression, like I can select my variable based on AIC, BIC, or like R square, any of them.
Whatever you want.
Say whatever.
Yep.
Yeah, thank you.
Okay.
Thank you, I appreciate it. Have a good day.
Yep, you too.